All right, so now we're going to discuss instantaneous rate of change. And remember from the previous video that whenever you see this term, rate of change right here, what that refers to in every single case is always slope of a line, okay? And what you'll realize is that you could actually replace this word slope in with rate of change, and what we would get would be instantaneous slope. That should help you kind of conceptualize what instantaneous rate of change is. Remember, when we looked at average rate of change, that's the same as saying average slope. That's basically saying what is the average slope of our line between our beginning point x equals a and our end point x equals b. So this is going to be, we're going to use somewhat of a similar derivation to get to this, but there's going to be some pretty significant changes we're going to make that's going to make instantaneous rate of change a very different quantity than average rate of change. So remember that when we were talking about average rate of change, we were always talking about rise over run. Anytime you were talking about slope, a slope of a line, you are always going to be talking about rise over run every single time. Only when we do instantaneous rate of change, it's a very special type of rise over a very special type of run. So we're going to introduce another variable here, this lowercase d. Remember from our previous video that the triangle shape, or the Greek delta, meant big change. Well, lowercase d means infinitely small change, okay? So if we went back to the example we used with a car going from 50 miles per hour to 60 miles per hour, well, the change to get there is going to be 10 miles per hour. That's a big change, okay? When we're talking infinitely small change, we would be talking about like 0.0000001 miles per hour, okay? Even smaller than that. Basically, infinitely small means as small as you can possibly get without actually hitting zero, okay? So therefore, dy means an infinitely small change in y, or an infinitely small rise. Dx means an infinitely small run. So when we talk about average rate of change, we're going to use those concepts of dy and dx to get a tiny rise over a tiny run. So therefore, we can think of instantaneous rate of change as a quantity dy over dx, okay? Now, this symbol in the next couple weeks, we're going to be using this over and over and over again. Dy dx is going to be prevalent throughout the rest of talking in calculus, so you're going to see it a whole bunch, all right? But let's talk about how we actually obtain these infinitely small rises and infinitely small runs. So if I go to this next page, you see right here, I got this function f of x. And what I'm going to do is we're going to be trying to calculate, okay, what is the instantaneous rate of change at that point x equals a? Well, to do that, again, if we want instantaneous rate of change, we have to calculate a slope. In order to get a slope, we need a rise over a run, okay? So we're going to use a bit different terminology. Instead of calling this point b, I'm going to call it a plus h, meaning that the distance between these 2 points is going to be this value h. H is therefore going to be our run. All right, so if we're going to look at rise over run and we want to calculate the instantaneous rate of change, so we'll call that instantaneous rate of change. At that point, well, rise over run is simply going to be this. If we want to calculate our rise, that's going to be the difference in our y values. So that'll be f of a plus h minus f of a. And our run is going to be a plus h minus a. Well, what do you notice happens in that denominator right there? You should see that these two a's are going to cancel right here. So what we're going to be left with is, instead of having this a plus h minus a down here, we're instead just going to be left with this value h, okay? Well, look at it right here. Remember I said instantaneous rate of change is infinitely small rise over infinitely small run. When we look at this value h right here, that doesn't look infinitely small to me. That looks like it's some noticeable change. So how can we make it infinitely small? Think back to the previous unit we discussed. What if we instead created a limit as h goes to 0? Therefore, if h is going to 0, remember, that doesn't mean h equals 0. It means h is approaching 0. If h is approaching 0, h is getting infinitely small, meaning we are getting an infinitely small run. And if we get an infinitely small run, we are going to be getting an infinitely small rise. So therefore, this is the equation that tells us what the instantaneous rate of change is at this specific point of x equals a. Now, it turns out there's another concept called the derivative, which is related to instantaneous rate of change, which we'll talk about in the next video. And we're going to have a slightly different variation of this equation to determine that. But it's important to understand really the concept that instantaneous rate of change is basically rise over run when run becomes infinitely small. And in math terms, this is how we say rise over run when run becomes infinitely small. Okay? So that's how we calculate an instantaneous rate of change. Now let's graphically look at what instantaneous rate of change actually represents and go to a Desmos file. So if we look at this file, again, kind of like the last one, an average rate of change, we start with some function. In this case, it's x squared. Now, a, that's really our starting x value. And what we want to do is figure out what is the instantaneous rate of change at that value x equals a, or in this case, x equals 0.5. You'll see that we have one blue dot right here at that point, a comma f of a. We also have another blue dot at the point a plus h comma f of a plus h. Notice right here that I said h equals 2. Okay, remember what we want to do when we calculate average rate of change or instantaneous rate of change is we want that h value to get as small as it possibly can. So a value of 2 is not very small. We want to shrink that down. Okay, so if you look at this red dashed line right here, if I ask you what do you think that red dashed line represents as this figure stands right now, what you should tell me is that, oh, the slope of that red line will be the average rate of change between this point, a comma f of a, and this point, a plus h comma f of a plus h. That's what the slope of that line represents. We're not interested in average rate of change. What we want is instantaneous rate of change. All right? So look right down here at this equation. What do you notice about this equation? Hey, that's the same equation that we wrote down on the previous slide when we were defining what instantaneous rate of change is, all right? So in this case, when our h value is something big, like 2, notice that we're basically just rehashing that whole concept of average rate of change, all right? But watch what happens if I take my slider and I bring h to go down. It's 2, now it's a little bit smaller. Okay, what do you notice here? Well, you might say, well, yeah, that still looks like the average rate of change. You've just made the run a little bit smaller. All right, but remember, what are we trying to do with instantaneous rate of change? We're trying to make run infinitely small. So if we make run go down, 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 down as close as we can to a value of 0 without actually hitting 0, what are you noticing that's happening? Okay, think about it for a second. What does it look like that line is approaching? Well, if we zoom in on this point, it might even be slightly more apparent. But if we zoom in here, we see that we still have those 2 points separated by that small distance, all right? But the geometry of the line with respect to the curve is changing a little bit, all right? If I make this h value even smaller, again, when we take a limit, we're trying to get it as small as possible without actually hitting 0. So let's say it's 0.0001. Now they're pretty much right on top of each other, but again, look at the geometry of that red dashed line. What is it doing? What it is right now is what we would call tangent. It's a tangent line, meaning that in a tangent line, you basically just come up, and at this point, our line is touching the curve f of x equals x squared, but it's not actually like intersecting it. It's not, you know, going through it like this as it was when we were looking at average rate of change. So graphically, this is what instantaneous rate of change represents. Instantaneous rate of change from this video, that is going to be the slope of the line tangent to the curve. So tangent to f of x at x is equal to a. That is specifically what the instantaneous rate of change of f of x at x equals a is giving us. It's giving us the slope of that tangent line. So remember in the beginning of this video when I said instantaneous rate of change really means instantaneous slope. The slope of this red line right here is the instant slope that that function has. It's if you had to say what is the slope at that very moment, that's exactly what it is. Now, when we move our point A to be slightly different, let's say I come up here and I change our slider for A to move up a little bit. And let's back up. Notice that as I move the point A, the equation still holds. We're still getting that red line as a line tangent to our curve at that any given point. So if I erase all of this stuff right here and we zoom out, we can see that as we move that point A around, if we hold true to that instantaneous rate of change formula, what we're going to get is we're always going to figure out what the slope of that line tangent to the curve at that point is going to be. So if I pan out like this, and now I move A back and forth, notice that that line is always tangent to that curve, okay? That's what instantaneous rate of change means. It means that the rate of change may be varying at different parts of the curve, but we can always calculate what it will be using that formula for instantaneous rate of change. All right?